The rail freight industry is big business, contributing nearly £900 million to the UK economy while supporting output of £5.9 billion. But amongst ordinary rail users, freight trains usually attract little interest, until, that is, there's an accident. At around 2 a.m. on the 22nd of June 2007, a wagon on a self-discharge train derailed on the approach to the River Great Ouse underbridge near Ely. The wagon was dragged onto the bridge, where it tipped over, along with others. Thankfully, there were no casualties, but until the wagons could be recovered and the bridge made safe, the Great River Ouse remained closed to waterborne traffic for several months. Considerable damage was done to the bridge structure, so much so it had to be replaced. The right-hand leading wheel flange on Wagon 16002, running over the railhead, was eventually identified as the cause of the incident by the subsequent RAIB investigation. But how had this happened? On-site examination and reconstructions identified the cause was the leading right-hand suspension sticking. This is known as frictionally locking up. It meant that only the tip of the wheel flange was in contact with the rail. As the wagon rounded the curve, only very small guiding forces acted on the flange. These were insufficient to keep the vehicle on the track. To help with the accident investigation, inspectors were able to identify a new way of using the industry's wheel checks data, which comes from line-side equipment that measures the impact upon the railhead of each wheel of a passing train and provides details of all trains with wheel loads outside acceptable limits. Investigators found this information could also highlight the diagonal forces on axles and could be used to identify potential issues with a wagon's load or its suspension. With that information, the RAIB team recommended that the wagon owner, alongside Network Rail, should look at the risk of a wagon suspension sticking and possibly causing a derailment. However, 2.5 years after the RAIB published its report for the Ely accident, in the early hours of the 26th of August 2011, investigators were called to another freight train accident, this time at Bordesley Junction in Birmingham.
The rear four wagons of the train had derailed as it approached the junction, run for about 100 metres derailed before it then came to a rest. We were called to site to investigate. On our way to site, we soon realised that we were dealing with the same wagons that had derailed at Ely. What we found was that the fourth wagon from the rear, its leading right-hand wheel had derailed as the train was passing over the junction.
They also found that the right-hand leading wheel on the fourth wagon from the rear of the train had derailed when its flange had climbed onto the railhead. The load on this wheel had been reduced by a combination of factors, one of which was that the wagon's suspension had probably locked up, just as had happened at Ely. Therefore, as a part of the investigation for Bordesley Junction, the inspectors set about finding out what had happened in response to RAIB's earlier recommendations.
What we found was that after the accident, Network Rail had initiated a programme of works to find out why these were locking up. As part of that programme of work, they'd instrumented 5 wagons and run them for a few months during the summer to identify if they were getting a problem with locking up on wheels. When they analysed the data from 14 different runs that the train had made, what they found was that during those 14 journeys, there'd been not just a few lockups, but they'd actually had up to 656 lockups during those journeys of the suspensions on those different 5 wagons. Some of those lockups were lasting for quite a long period, up to several minutes, although the average time for a lockup was around 25 seconds. So this would be a period when the suspension wasn't working, it wasn't responding properly. Now that the extent of the problem was known, Network Rail and the wagon owner had identified some modifications that they could make to the suspension to prevent it from happening, and they'd trialled those modifications on a number of wagons. During the trials, they'd found a 75% reduction in the number of lockups that they were getting, and also the length of time that the suspension was locking up for was much reduced as well. However, by the time of the accident at Bordesley Junction, none of the rest of the fleet had been fitted with these modifications, so the wagons that had derailed at Bordesley didn't have these modifications in place. Experience showed that these wagons weren't derailing everywhere they went. So although we had suspensions locking up, there was another factor that was causing them to derail. So as part of the investigation, we also did a survey of the track at Bordesley Junction, and what we found was something called a track twist. One of the things that is measured in terms of the track's geometry is the height difference between the two rails. This is a term known as cant. But when the difference in cant changes very quickly, that's what's called a track twist. So the rate of change between the height of the two rails is much quicker than it should be. And that can cause wheels to be unloaded. And what we found at Borsley Junction was there was a track twist in one direction unloading the wheels, which was probably causing the lockup of the suspension, quickly followed by another track twist in the other direction that then unloaded the locked up suspension, and then that led to our derailment. To measure the condition of its track, Network Rail has a fleet of trains that are called track geometry recording trains that measure all of the track's geometry, including things like cant. And from the cant, it automatically calculates what level of track twist is there. What we found when we did the investigation was that these trains were running approximately every month over Borsley Junction, and they were indeed finding track twists. However, Network Rail maintenance were going out to respond to these track twists, and when we investigated further, we found that they were actually repairing the track in the wrong place. They were repairing joints either side of where the actual track twists were. So for a long period of time, these track geometry faults remained uncorrected, and were in that state at the time of the derailment at Borsley Junction. During previous RAIB investigations, we found instances where there have been repetitive track geometry defects that haven't been corrected, and as part of a previous recommendation, we called for Network Rail to have a system to monitor repetitive track defects so that they could ensure that they'd been effectively repaired. Part of that work involved Network Rail implementing a system nationally where they could provide their staff with a system that would allow them to track repetitive track geometry faults and therefore avoid this kind of situation occurring again.